Can you hear me? Oh, I guess not. You probably wanna unmute yourself. Ah, there it is. Yeah, cool. So, a long story short, this is my first stream. I'm also doing that recording for a future practices and whatnot. Let's see if we're gonna get anybody else. All of them. All of it. Yeah. Problem one. We're talking about the same problem one. The 4-4. Or you're talking about board problem one. I got 345.6. Oh, bending. My bad. It should be 4171.2 psi. For my eye, I had 1/12 times 1 inch times 5 inch cube. Negative 1,800 pounds for the shear, and then 28,800 pounds inch. Did you make sure that you're doing not 4 inches but 4 feet? Yes, because the whole thing is uh, so a whole thing is about 5 feet long. Okay, and he says determine the normal and shear stress at 1 foot away from the right and 1 inch from the top. Okay, so in order to stop confusion with the units, I just did everything in pounds and inches. And it also depends where you put your origin at. I went from left to right. Mm-hmm. Mm-hmm. Okay. While you do that, I'm gonna drop the announcement that I am starting. Yes, I do feel confident about the test. Also, can you keep talking? I want to make sure that I am getting or not getting your voice in a recording. Okay, I am not getting your voice in recording. This would be a lot of one and conversation. Awesome. Yeah. So then I'm gonna ask majority of people to refer to the chat, and let's say I'm gonna ask you to ask questions in quiz study chat. I've been asked many requests on share homework and answer a couple of questions about homework and exam prep. So I just decided that I'm gonna start from scratch by literally doing one problem at a time from all the homework being done. If that is fine with you guys. Sweet. So without a further ado, I'm gonna start with the homework number one, and the question just was primarily about board problems. I will probably toss some other complicated problems from a textbook, mostly because I find them fascinating. Okay, a little disclosure: I am recording a session, so I could see what and how this whole thing being a streamer works, and we did a test of none of your voices are being recorded, which is a good thing. The bad thing is that if you guys are gonna ask me questions via the microphone, I'm it will look like a one and conversation. So if you do have a good questions, please drop them in a quiz study a text chat. Okay, so we gotta start with problem BP01 from homework 01. I'm just gonna say that this is homework number 1. Okay, let's say it says a simply supported beam of length L, which means I'm going to start with my free body diagram. And the simply supported beam looks something along these lines. It's going to be fixed at the point right here, and it's going to be supported right here. A good example of this would be, I don't know, a bridge, where we have things like that. We have a ship right here. The idea of this is that the beam is going to be fixed at this point, so there will be a resultant in the y, and there will be a resultant in the x, and it's free to move. And then this guy will be supported only right here, going up, and it will be free to move left and right. Sorry, that should be B. Left and right, because due to thermal expansion, thermal contraction, other stresses, and we want to prevent internal bending and internal collisions inside of the beam. Okay, so simply supported is a and x, y and x on one side, then a y on the other side only. Okay. It says it is loaded with a uniformly distributed load of W over the length. So, again in blue color, across the entire beam, we're gonna have a distributed load of W, or I'm also gonna refer to that omega, because every time I write it in cursive it looks like omega, and I'm gonna call that omega. Gotta mention that the whole thing is L. And another piece of information that we need to know is that any concentrated load of F, a third of length from the left. So I'm gonna use this color. Somewhere right here will be an F with a third of L from here. Okay. Another important piece of the free body diagram would be a reference of frame, and I usually prefer up being a positive and from left to right being positive. So I'm gonna do it like this. Okay. Since this is a question from the beginning and we haven't studied anything in terms of singularity functions, I'm gonna solve this like any other static problem. So my sum of the forces in the y going up being positive will be RAY plus RB minus F minus, I prefer doing that in terms of calculus, so I'm going to say integral from 0 to L of omega dx. That would be 0 of rho. Sum of the forces in the x going right will be positive. There's only one force, Rax, and that is 0. And another important piece of information, moments going counterclockwise being positive, moments at the point A. I'm gonna read out every single force, and probably 2 of them will be unnecessary and redundant. Such as, for example, I'm gonna have causing counterclockwise rotation. I'm gonna have RAY 0 away from the point minus RAX also 0 from the moment. Another thing going counterclockwise would be RB at a full length minus F going clockwise on the distance of the third of a length, and then minus integral from 0 to L of load times position of the load times little bit of change in the load. Okay, and sorry, of course all of that is going to come up to be a 0. Okay, so now all I gotta do is find my, so the job is to find what is my RAY and what is my RB, since I know that my RAX is 0 and it's not doing anything important or doesn't do anything at this point at all. Right out of the way, I can cross out this and this because they're just 0, they're not important, and all I'm left with is RBL minus FL over 3 minus omega is a constant. I can take it outside, going from 0 to L of x dx equals to 0. My primarily objection is to solve for RB, so I'm gonna move everything with negatives that to the other side, and at the same time do the integral. It will be RBL is equals to FL over 3 plus omega L squared over 2. Okay? And now I can just divide everything by L, the left and the right side, and I'm left with a RB is equals to a third of F plus omega L over 2. And I found my first resultant of force. And now since I know that, I can do my RAY. I'm gonna say that RAY. I'm gonna substitute my found force for my RB. It'll be F over 3 plus omega L over 2 minus F minus integral of omega dx going from 0 to L equals to 0. I'm gonna isolate my RAY by moving everything to the right and computing integral at the same time. I'm gonna get my RAY equals to F plus omega L minus F over 3 minus omega L over 2. And if I combine like terms such as these two guys and these two guys, I'm gonna end up with a 2/3 of F and omega L over 2. And those are questions that we've been asked to solve. Any questions about this problem so far? And if I do go fast, please let me know. I will slow down and explain things probably more coherent. Okay. All right, cool. So I believe we have only one problem in a homework 1, BP1. Yes. So let's go and try and do board the problems from the question 1. So draw the values. Okay, those are the questions from the a video. So I'm just gonna copy down the question with a free body diagram since I don't have access to the video at the moment, and it's gonna eat up too much time looking it up anyway. Cool. I'm not gonna explain how I came up with the free body diagram because it came from the video, and once again, it is simply supported beam, means we have only one fixed point with a pin, not allowing us to move up, down, left, or right, and we have support not allowing us going up or down, but allows us to go left or right, as the previous problem. And I believe this was another section where we didn't get to study singularity function, so I'm still gonna go with statics equations. It does ask us to draw shear and moment diagrams showing all the values and write the moment equation for each section of the beam. I personally cannot do just the moments without doing a shear, so I'm gonna do both primarily because I physically just cannot. It is too much to ask for me, and for some reason my OneNote is being little poop. Give me just 1 second. There. Better. So, once again, statics. All the forces 0, all the moments 0. So some of the forces in the Y going up positive would be resultant in a Y. Oh, am I not? My bad. Thank you. Sweet. Thank you very much. So, once again, our forces going up would be A, Y, and B. The forces going down would be integral from 0 to 6 of 10 kilonewtons per meter times change in length minus 20 kilonewtons. Everything adds up to 0. Sum of the forces in the x going to the right being positive would be ax being 0. Sum of the moments around point A counterclockwise being 0. I'm not gonna explain ax and ay because they're just at the point where we're going about. They make no impact. The only things that do make impact would be the force B on the distance of 12 meters going counterclockwise minus 20 kilonewtons times 9 meters going clockwise, and then minus integral from 0 to 6 of 10 kilonewtons per length times its position times change in length also adds up to 0. So from here, I'm just gonna solve for B. I'm gonna move everything on the opposite side and integrate along the way. I'm gonna get 12B, horrible B, still B, times 180 kilonewtons meter plus 10 kilonewtons per meter times 1/2 6 meters squared minus 0 meters squared. And this turns out to be 12 meters times B is equals to 180 kilonewtons meters plus 36. 36 divided by 2 would be 18, right? Right. And multiplied by a 10 would be another 180 kilonewtons meter. So 12 meters B adds up to be 360 kilonewtons meter. Therefore, B comes up to be 30. That's dirty 30. 30 kilonewtons. And since I know B, I can also find the AY. Would be moving everything from here to the opposite side. I meant to say from here. Would be 20 plus 60 minus 30. And that should come up to be 80 minus 30 will be 50 kilonewtons. So far, so good? You should be able to go click on stream. Okay, I'm gonna wait for that guy to join in, and we'll see. We shall see what's up. All right. And now, since I know my A, Y, and B, I can start dissecting my free body diagrams on the pieces that are important for this problem. So there are three places I'm gonna chop in, and those will be in the places where I have some sort of change. Okay, I definitely have from 0 to 6. I have a distributed load. Okay, between 6 and 9, I have complete distributed load. And then from 3 to 12, I have distributed load and applied force at 9. Okay, so for that, I am gonna say that for the x values between 0 included and up to 6, I'm gonna have a beam with resultant AY and distributed load going across the whole thing with a 10, I believe it was 10, yeah, 10 kilonewtons per meter. The frame would be the same. This would be Y and this would be X, where this distance right here would be X. Oops, X. The internal stuff, so let's make it look like I actually cut it up into pieces right here. I actually snapped it. On the internal, I'm gonna have shear going like this. I technically do have an AX going to the right, but since it's 0, I'm just gonna say that there will be technically a normal board in here, but since force is 0, the normal is also 0. It's just over there for completion of the image. And I also have internal moment going this way. Okay, so the same idea here. I'm just gonna say that I have some of the forces in the Y going up positive. I'm gonna have AY, which is 50 kilonewtons. Going down, I'm gonna have 10 kilonewtons per meter times X. Technically, I could say that that would be an integral from 0 to arbitrary x times dx, but that's gonna integrate to the simple 10 kilonewtons per meter times x minus the shear as a function of x equals to 0. Okay, and from here, all I can do is I'm gonna say that my shear of x will be 50 minus 10x, everything in kilonewtons. The moment equation for that would be, I'm gonna take the moment at the point A, would be going counterclockwise, would be that moment as a function of x, and I think it's gonna go clockwise. A moment will go counterclockwise. Other stuff would be clockwise. Be an integral from 0 to x 10x dx, and then minus the shear force times the x distance away. So if I pinpoint right here and I go around here, that v of x also makes the impact on that. Okay, so we get m of x minus 1/2 10x squared minus 50 minus 10x times x equals to 0. So that comes out to be, moving everything on the other side, we get positive 5x squared plus 50 minus 10x times x doing a simple math would be 5x squared plus 50x minus 10x squared will be negative 5x squared and plus 50x. So that's from 0 to 6 only. Now, to do the other will be from 6 to x to 9. Still gonna have a beam, just a little bit longer. Cut it out right here. I'm still gonna have another V right here, and the moment going this way. Shear force will be completely distributed. Resultant AY right here. And another important piece to keep in mind is now my x is between 6 and 9. So my x is actually only within this piece, and this guy right here is fully 6. Just gonna say that positive y here, and then positive x here. So exactly the same process, exactly the same steps, except we're gonna have some different values. We're gonna have some of the forces in the y will be 50, going down will be negative integral from 0 to 6 tan dx minus v of x equals to 0. So v of x comes out to be 50 minus 5 times 36. Let me crunch that into a calculator. I get negative 130 kilonewtons. Now, the thing that I like to do about this is I want to double check that I'm actually coming to this value as I plug in 6 into here. And as a matter of fact, I'm actually may not get that. I'm going to get negative 10. Oh, I'm big dum-dum. I'm not squaring. It's just 10 times 6, which is negative 10. And now I do get the same thing. Cool. Negative 10 kilonewtons. And of the moments, some of the moments at A, going clockwise, this was going up. We're going positive moment at X going counterclockwise. Minus integral from 0 to 6 of 10x dx, and I accidentally calculated that up here and made a mistake, my bad. And then minus v of x times 6 plus x. Hold on a second. Oh wait, it is just x, right? Because I said that x is between 6 and 9. So times x equals to 0. So then the moment of x is equals to, this will be 5 times 36 plus negative 10 times x comes up to be 5 times 36, 180 minus 10x. And again, just like right here, if I set my x being 6 right here, I should get the same value as if right here. So if my x is 6, I can plug in a 0 here, and I should get the same values between the moment in a previous one and the moment right here. So just a quick check. or actually plug in x being 6 here as well. Should be 180 minus 10 times 6. Also get 120. Cool. So these guys will line up. And then the last piece is x being between 9 and 12. I believe we had another one being right here. So now this guy would be a 6, this guy would be 3, and then this distance would be x. Gonna go positive y right here, positive x right here, 10 here, and we had a 20 kilonewtons down. Exactly the same process. A was 50 minus 64 distributed minus 20 for applied minus v equals 0. So v of x comes out to be 50 minus 60 is negative 10. Negative 10 minus 20 will be negative 30 kilonewtons. Now, the reason why this number is not gonna match up to the number before is because there wasn't really any smooth transition from one to another, but a change is exactly as a force being applied. So if we had negative 10 before and we applied extra more going down, we're gonna have equivalent of the change in a shear. So we do get the negative 30. Coming up to that, the same idea would be the m at the point A going up would be moment minus 5 times 36, as we already said, it will be 180 minus 20 times a 9 minus negative 30 times an x equals to 0. So then the moment in x comes up to be negative 180, and then another little 180 comes out to be 360 minus 30x. And here I can double check my answer again. I can plug in 9 into here, and I should get a 90. I get 90, and then if I do the same thing right here, I get 360 minus 30 times 9, I get 90 as well. Sweet. Now here's a cool thing. We don't have any moments applied on either of the edges, so of the moment at 0, at the moment at the full length should be the same, and they should come out to be 0. The same thing with the shear forces. If I don't get the a negative value of the resultant force at the end, I probably did something goofy, and I don't, and my shear does not come up to be of 0. But since my B is positive 30 and my shear is just negative 30, I should be good. Now, to graph those guys, you're literally gonna cut every single your every single little graph you make into segments like you did for the calculation. Here like that. And I'm just gonna add some lines right here. And add some lines right here. So initially for my shear being right here, I started it in 50 and I went down 10 times x for 6. So let's say this would be 50. And then 2, 4, 6 right here. I'm gonna get, actually, might as well do it incrementally. 50 here. If I subtract a 60, I get negative 10. I'm gonna end up right here. Gonna draw the line from here to here. Then for the next 3 up to 9, I'm gonna carry the same 10. So I'm gonna come up to be right here. And then for 3 from 9 to 12, I'm gonna drop down another 20. And I'm gonna end up at negative 30. Go till 12. And I'm gonna go up 30 because that's what my resultant force is at the end. I'm just gonna say that I initially went up 50 from the 0 to make it coherent. Cool. This was shear with respect to x. In x, everything was in kilonewtons. Kilonewtons. Now about this guy right here. Negative 50x squared plus 50 will actually mean that I'm gonna start at 0. And I'm gonna be going positive. I'm gonna be increasing, and then I'm gonna be decreasing, because if you guys remember from calculus, the moment of x is just a integral of the of vx. So then if my vx is equals to derivative of the moment of x and my vx equals to 0, which happens right here, I'm gonna do a flat line. Okay, so 2, 4, 6 here, and I'm gonna be looking something like this, where we can calculate this of value here by finding that at x equals to 5, we had a shear being 0. We can plug in that 5 into our moment equation and find what that value is. The moment equation for that segment is right here. Negative 5 times 5 squared plus 50 times 5 comes out to be 125 kilonewtons meter for x being 5. I'm just gonna draw it with meter, seeing that here's the maximum. Something like this. This would be 125 kilonewtons meter. Cool. And then from 6 to 9, I'm gonna be decreasing at the rate of negative 10. And then from 9 to 12, I'm gonna be decreasing at the rate of negative 30, or decreasing at a rate of 10, decreasing at a rate of 30. If I will be decreasing at negative, that means I'm actually increasing. Doing a quick calculation right here. This would be a 90, I believe. 180 minus 60 will be 120, right? So I do line up at this point here. This would be 120. If I plug in 9 into the same equation, minus 90, I should get a 90. Just gonna put it a little bit up higher. And then from 90 at the rate of 30 times 3 would be another minus 90, so I get to 0. Where I get to say that M max is equals to 125 kilonewtons per meter at the X is equals to 5 meters. That sums up the BP1. Any questions so far? Maybe you guys need me to scroll up somewhere so you could examine that a little bit better. And I did see a quick question at a quiz study. What's the sign convention for that again? What problem is this? A problem was a BP1 from the second homework. Looks like a face of something to remember it. This is BP1 from. What do you mean by a face or something to remember it? I believe it was a routine pudding. Yeah. Yes, there is a sign convention, and I assume you want it for a shear, and yes, shear in a moment. Cool. Yes. So let's say I'm just gonna cut a beam at the both ends. Oops, that was thin bin. And conventions are such that if you look, if you cut right here, your a positive shear will be going down, and your positive moment will be going counterclockwise. So a plus here and a plus here. However, if you do look at that from perspective of your reference, then your V will be subtracted. Okay, but if you do cut it, and I'm gonna make that in other color. So let's say we're going from here, this is Y, and then we're going right here in X. If you do cut it from the left side, then your shear, I'm gonna do it in green, should be going up, and then your moment should be going clockwise. Is that what you meant to ask? Yeah, okay. I see another question coming up. Okay, so what did you get for the moment and Ben is just for BP1? Okay, can we actually hold off on questions on problems that are gonna come up in some upcoming future, or do we actually gotta do it now because people gotta go places. Okay. Okay. We will get to a BP1 on the last homework. I guarantee you that. Um, from homework 2, we have another BP2. Do we need to go over that, or based on things that I shown, we good, and you guys can get that done as well? Okay, I can actually promise you and guarantee you that singularity functions will appear on exam. But if there are no questions about BP2, we can actually go to the third homework, and there is a question of the singularity functions. Let's see another good question coming up. Most likely singularity to transfer and to normal stress. Okay, so I guess there's no need for a BP2, huh? Mm-hmm. Okay. That is very true. That is actually we did, yes. And I guess I'm gonna cover those as well as we will get there. Uh cool. There are a lot of BPs to cover. Do you guys have any preference which one to do? Or should I just bite the bullet and do them all? Okay. I'm actually still gonna do two of them just because there are two simple cases we've covered, and they will all have their own unique thing. But I'm gonna just start with the BP2 then. It was another video problem. I'm just gonna copy down that with a free body diagram. Yeah, the problems that were assigned in a first homework that are with like strings and the dampening the frequency, undampened the frequency, impact, and all that good, the good jazz. Yes. Oh no. All right. Give me 1 second. I gotta close this thing up again. Cool. So we should be back on the board. Do you guys know how to open and close a singularity functions, or this is something that I do need to go over. Okay, so what do I mean by open and close? If I'm gonna do it of the way how I set up everybody diagram at the moment, with my s going to the left as a plus, I'm gonna have to open it only, maybe meaning that I'm gonna start a signal and then a signal is gonna end exactly where a beam is gonna end. But if I do set it up going y being positive here and then x being positive here, I'm gonna have to open a signal for here and then close it off for here. Okay, cool. So I'm actually gonna start with that and I'm gonna redo it either way. And as a matter of fact, the answers will still be the same regardless. So a beauty of singularity functions is you get to do all of this math, all of it, in a one equation. So to, to start that, I'm just gonna do two things. I'm gonna say that there are no shear past the length of the bar, and there is no moment applied past the length of the bar. Also, there will be no change in position at the beginning and at the end of the beam. However, I cannot say so about a white prime. Don't know that, and don't know that, because from a physical perspective, the beam is gonna be looking something like so, over exaggerated, really over exaggerated, where the slopes right here and slopes right here are not zero at all. Okay, so having that in on a paper is handy. So yes, right here I have a 12 plus and a 12 plus. So it's like the beam, but a little bit further. So somewhere right here. It's a little bit past it. Okay, so 12 plus is a 12 plus change in an x in increment small, a change. So this is kind of slightly bigger but yet equal. Okay, so actual the functions, if I count this being 0 and I go from left to right, I'm gonna start with the loads. Also, when x is less than a, it's 0. I had trouble because he didn't mention that. X is less than a. Do you mean to the left or to the right? Yes, 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 exactly. So I guess it's important to say how singularity the functions operate. Singularity functions. If we have a coefficient, if we have x minus a here to the power, this guy is called a switch. It can turn on. So imagine a switch. It can go on or it can go off. Did I mention in the lecture? Yeah. So, case 1. When x is less than a, then the whole thing of x minus a to any exponent is usually, is actually equal to 0. It's a switch off. If we have two cases for x being equal to a, and those would be if x minus a raised to any to the power where n does not equal to is 0, we have switch off, and then we have x minus a raised to the power of 0, then we have switch on, and this would equal to 1, simply because 0 to the power of 0 is still 1. Okay, and then for anything to the x being greater than a, of course, if n is equals to 0, then x minus a to the n is equals to 1. And then if n is greater than 0, then x minus a to the power of n equals to literally whatever x of value is minus a raised to whatever n of value is. Okay? And another thing is that if n is less than 0, then the whole thing equals to 0. It is off. If x minus a, if n is equals to 0, then C parts 2 and 3. And if n is greater than 0, C parts, butcher that, C parts 1 and 3. Does that explain singularity functions in a nutshell? Cool. All right. I'm just gonna copy this down and put that right here so I could actually see what my question is. Oops. I'm just gonna drag it down. Somewhere like so. Cool. Then, if I begin with my load, so load, it is a q of x, and it actually explains what our distributed loads are in here. So I definitely have going down. Actually, let's begin with going up. I have RA x minus 0, but since RA is a force, it is not a load, I'm gonna put it to the negative 1. Going down, I'm gonna have W, and then I'm gonna open a bracket for purpose because I begin having it on at x minus 0, but I also gotta shut it off at x equals to 6. Okay, so this means on, and then this would turn it off past 6. Okay, any good questions about on and off here? And it's actually going down, so it's minus. This is what I meant to say, to turn in a load on, and then as we go on, to turn in a load off. It's essentially as if I drew it out like so we have it on for the whole beam, and then we're gonna put equivalent going halfway the beam in opposite direction. Okay, cool. I got a thumbs up saying it makes sense. Cool. And continuing on, I'm just gonna move my cue to the left a little bit so I could fit everything in one piece. Just gonna put that right here. And I'm gonna say minus 20. Should have actually said this would be a negative 10, but it doesn't matter. You can plug in values in the end. 20 going down at x, and we're gonna begin that at x equals to 9. Since this is a load, since this is a force, we're gonna put it to the negative first, and we're gonna shut it down by RB at x minus 12. Since this is also load, we're gonna put it to the not load of force. We're gonna put it to the negative first, and from here your setup is done. All you have to do is just integrate up until a moment, and then through that you're gonna find your shear and moment equations, and you're gonna find your RA and RB. Okay, so as I integrate along the way, I get V of x is equals to RA x minus 0 to the 0, and the reason why a 0 is because of singularity functions do not apply same calculus laws up until you hit the power of 1. If you hit a 1, then you can treat it as a function. Then we get negative 20 x minus 0 to the 1 minus x minus 6 to the 1 minus 20 x minus 9 to the 0 plus RB x minus 12 to the 0. And gonna integrate that again. I'm gonna put it right here. M of x is equals to RA x minus 0 to the 1 minus 20 1/2 of x minus 0 to the 2 minus 1/2 x minus 6 to the 2 minus 20 x minus 9 to the 1 plus RB to the x minus 12 to the 1. Cool. So now what I get to do is I gotta plug in 12 into each and of single equation here and here, and find RA and RB. So here I'm gonna get 0 at 12 for RA. 12 minus 0 is 12. 12 to the power of 0 is 1, so it's just RA minus 20 times 12 minus 6, because 12 minus 6 is 6. 6 to the 1 is 6. And then minus 20 times 1 plus RB. And then another 0 is going to equal to RA times 12. Have a little question up there, I see. Why is it negative 20, not 10? Did I screw up? I screwed up. I am so sorry. This should be negative 10. This should be negative 10. And this should be negative 10. Thank you for catching that mistake. Thank you very much. Then RA times 12 minus 10 times 1/2 of the 12 squared minus 1/2 of the 6 squared minus 20. 12 minus 9 would be a 3. A brain fart, my bad. Then RB times 12 minus 12 raised to the 1 would be 0. So this whole thing is 0. So from here, I can find my RA, and then once I find my RA, I can find my RB. So 12 RA is equals to 5 times 144 minus 36 minus 60. So 12 RA comes up to be comes out to be 40 for 80. Therefore, RA comes out to be 40. Okay, I believe I got 50 last time because this is exactly the same setup as before, right? And we do get 50 before time. I probably goofed and made another silly mistake somewhere along the way. Nah? Yeah. I found a mistake. This should be a plus right here because this was minus, this was minus, so that was plus. I found my mistake. I just didn't carry out the numbers right. So this should be plus. So this should be actually 600. And then if I divide that by 12, then I get 50. Sweet. Yeah, someone else got 50. Sweet. So then from here I can find my RB by saying that I have 50 minus 10 times 6 minus 20 plus RB. Everything equals to 0. So we get RB equals 20 plus 60 minus 50 equals to 30. I believe everything was in kilonewtons. So now, since we have all of their values, we can plug them into our moment equation, and we get 50 times x minus 0 to the first minus, I'm just gonna carry out 1/2 from there, will be 5 times x minus 0 squared minus x minus 6 squared minus 20 x minus 9 to the 1, and then plus 30, 30 x minus 12 to the 1. Okay, this thing also equals to e I y double prime of x. This thing right here is actually should have been covered in your material science or strength. I do not remember explanation of that, so I'm not gonna jump into a rabbit hole explaining why this is that. You just make a note in your exam sheet saying that this is that. That's it. And then from here we get to integrate a lot more. You have to say that ei y prime of x is equals to 50 over 2. Was there a value for that was a constant? No. So during the calculation a shear and a moment, there was no additional constant over there, specifically because of this givens right here. Because every shear ends up being 0 after a beam, and then every moment comes out to be a 0 after a beam as well, there are no constants being added. There will be no constants added during the first couple of integration. The only constants you might see, as we will see here actually, are gonna be during integration for a y prime and a y. And the problem would end with 1 over ei in its right. That is very correct because we don't have the ei. We don't know if it's made out of steel. We don't know its shape over cross section, so it will be in an ei. Cool. Let me just double check something. This was that is not important. Moving on. So integrating this, we get 50 over 2 x minus 0 squared minus 5 of 1/3 x minus 0 cube minus 1/3 x minus 6 cube minus 20 over 2 x minus 9 squared. Oops, that should be a bracket. Squared plus 30 x minus 12 squared. 30 over 2 x minus 12 to the second plus c1. And since we know that this is a simply supported beam, we definitely know that the slopes at the edges are not going to be a 0, so we cannot get rid of c1. So now we're going to integrate once again. ei y of x is gonna be 50 over 6, because 2 times 3 will be 6, x minus 0 to the third, minus 5 times 1 over 12, x minus 0 to the fourth, minus 1 over 12, x minus 6 to the fourth, minus 20 over 6 x minus 9 to the third. My brackets looking more and more like parentheses. That's gonna deduct the points from my exam because he is very picky about that. 30 over 6 x minus 12 to the third plus c1x plus c2. And now we get to acknowledge that y of 0 and y of 12 equals to 0, and we're gonna use these two givens to find c1 and c2. Okay, so at a 0, literally everything turns to 0 except c2. So 0 is equals to 0 minus minus 0 plus C2. Drawing conclusion, C2 is 0. Cool. Then at x equals to 12, we get another 0 is equals to 50 over 6 times 12 to the power of 3 minus 5 over 12 times 12 to the power of 4 minus 6 to the power of 4 minus 20 over 6 times 3 to the power of 3. 30 over 6, this should be 0 plus C1 times 12 plus 0 for C2. So only thing we gotta do is to find our C2. I'm just gonna simply quickly crunch this whole number into my calculator. See what I get. 50 over 6 times 12 to the power of 3. And that comes out to be 6210 plus 12 C1. Therefore, C1 turns out to be, divided that by 12, it's gonna be negative 517.5. Okay, so then our equation comes out to be EI y of x is equals to 50 over 6 x minus 0 to the power of 3 minus 5/12 x minus 0 to the power of 4 minus x minus 6 to the power of 4 minus I believe that was 20. Yes, that's 20 over 6 x minus 9 to the power of 3 minus 5. My bad. There should be plus 30 over 6 x minus 12 to the power of 3 minus 517.5 x. The problem's question was to, using a singularity function, determine deflection in the middle of the beam in the video above. So the middle of the beam is, the bodies are change in y at x is equals to 6. Okay, so as I plug this stuff in, y of 6 is equals to 1 over EI, as someone mentioned before, times 50 over 6 times 6 to the power of 3 minus 5/12 times 6 to the power of 4 minus 0 to the power of 4 minus, this goes to 0 because 6 minus 9 is negative. Yes, this would also go to 0 because 6 minus 12 is also negative, and then minus 517.5 times 6. So if we calculate all of that, we are gonna get 50 over 6. I get negative 1845 divided by EI. Keep in mind that E, if it's in metric system, it would usually measured in gigapascals. So it would definitely cut it down to at least 1,000th of a meter. And then EI, depending on what we calculate that in, depending on a cross-section, would either gonna bring it up to 1/10 of a meter or bring it down to another good a millionth of a meter. Okay? Any questions about this? Overall, maybe I should go back and explain something a little bit more in detail. I like how someone just spelled out my name on entire video. Sweet. So how did I get C1? We got C1 through here, knowing that y of 0 and y of 12, meaning that at the edges of the beam right here, being supported, and we right here also being supported. So changing y, if I would have drawn my x being right here and y being right here, there will be no sag at the origin and there will be no sag at the ball. So C2 can come out to be 0 by plugged in x being 0. And then C1 came out to be its number when we plugged in x being at 12. So this is 12 right here and 0 right there. Unfortunately, this video will be contaminated of drug abusing because I do smoke and I do abuse caffeine. I hope I'm not gonna get kicked out of school for that. Though, nevertheless, I know, right? You never know these days. These guys will get to you about everything. So, we did a simple beam, a simple support beam. Let's do one with a cantilever beam where we find deflection. So how about BP2 from homework 4? We will get to the BP2 homework 4. I'm not gonna do BP3. I am gonna say one thing. I'm just gonna copy down the free body diagram because there are a couple of things that I do want to point out if it was missed out on a lecture. This guy can be done exactly the same way. It doesn't matter which way you go. If you go from left to right, you're gonna only turn on here. Oops, right here. And then if you go from left to from right to left, then you're gonna have to turn this on and then off as we did that before. Okay. So only a difference between this guy and that guy is if we are gonna sag, let's over exaggerate that again, we're gonna sag like so. If you saw something inappropriate, it's only on you. So things to keep in mind. Shear at the full length plus is equal to 0 because there is no force applied outside of the shear, outside of the beam. The moment at the length plus is also 0 because there is no external moment applied past the beam. And by past the beam, I mean right here. And we don't have a slope change at 0. And we don't have sag at 0 as well. So it is safe to say that our C1 and C2, as we go from the acceleration to the change in angle to position, all gonna be 0. Okay, any questions about that? Awesome. I think this was all from the homework 3, BP3, BP4, identical problems. Almost. Homework 4. I actually do have a questions to you guys about BP1. Do any of you need to see how BP1 is done? Almost. It is right, except by surprise, if I took my moment to a right, going counterclockwise, I got change in y being positive. So I actually ended up looking like so. If any of you can second that, that would be awesome. Okay, so you probably got a sag going down. Okay, gotcha. Also, I feel very sorry how you study over there with all that the concert behind you. Um, cool. I guess yes. I did had a couple of moments when I had neighbors park a car right by my window as I was taking my exam. I was unhappy. I know. I had to send an email. Sir, I'm about to come and give me a murder. Can I please retake exam? The guy was nice enough to cancel a time limit for me. Anyway, so a BP2, a beam with a diameter G and supported at a thirds and 2/3 of the length is loaded with F at X equals to 0 with distributed load for L over 3 and 2L over 3 with a moment at X equals to L. This is another problem where you would have to assume how you're gonna draw your moment, right? Unfortunately, he doesn't say how you're gonna have to do it. Question is no singularity for this problem. Honestly, up to your choice. Really up to your choice. I like singularity of functions because they give me a full picture in literally one equation. Right. And yes, as a person in the chat says, they do like it only for a deflection and change of slope. I mean, that's the only way you can get there. But you can also do a free body diagrams to find your reactions. Yeah, sure. So a beam with the diameter d, gonna have to kind of improvise here and try and draw a 2D a 3D image on a 2D plate. Reasons why I don't like 3D video games. Exactly because of that, it tosses me off so bad. Unless it's a Valve, then it's not their thing. Supported somewhere third way here and a third way here. Singularity, there is a longer way in strength. Lol, singularity is way easier. Godsend indeed, my guy. So we are experiencing a force of F right here. We have distributed load going along right here. And we have applied moment right here. I always draw my moments going counterclockwise, mostly because it's just convention. It's a saying saying you can't teach an old dog to new tricks. I'm only 24, but I do consider myself an old dog. Same counterclockwise, positive always. Yes and no. And if you guys have been paying attention to the lecture, there is a great way he described it. Imagine this thing actually bending, okay? If you have a thing and you will try to apply a bending moment right here and right here going this way, you kind of gotta make it a smile, okay? It's gonna look like that, okay? We have a happy face. And we have a happy face, our mood is positive. It's a positive for a nose. But if we're gonna have a beam, and we're gonna apply the moments going this way, this moment's gonna make this beam frown, right? We have a sad face, right? And we have sad face, we are in a negative, shitty mood, okay? So this is only useful if you guys gonna try and write out your singularity functions right off the bat. Started in with my bad. Started in with a loads. Okay, if you're just gonna do a free body diagram and just go moment, load, force, sum of the forces, sum of the moments, everything equals to 0. Whatever you get, you get. Okay? I'm just gonna say that this is a moment. So, how should I do this? Everything who's for singularity functions, please put thumbs up in the chat, and everything who is for free body diagrams, please put thumbs down in the chat. There's not that many of us, we can do it. That's 1, 2, 3. Hi. Okay, so we have 6. We are way past average, so singularity the functions it is. I'm just gonna take this and move this somewhere out of the way, right here. is gonna look at me and make me smile every time I study up late at night. I'm gonna refer to this section nightly now. Cool. So starting with the Q of X. Right off the bat, if I will start right here, I'm actually gonna do this in yellow. Starting right here. I get negative f at x minus 0 raised to the negative 1. Then I get positive RA at x minus length over 3 raised to the 0 minus omega, opening up, would be x minus L over 3, closing it, oops, that should be negative 1, my bad, closing it down, turn it on, and then turn it off, gonna be L minus 2L over x minus 2L over 3 to the 0th power, plus RB at the x minus 2L over 3 to the negative 1, and of course I ran out of space. And of course that guy didn't pick it up. This was right here. And then a positive moment at x minus L to the negative 2, because a difference in a power between Q and M is 2. Integrating that along the way, I should refer that V at L plus is equals to the moment at L plus equals to 0. And the only things that I do know is that y at L over 3 and y at 2L over 3 equals to 0. Okay, definitely cannot say anything about where the change in angle would be. It's 0, so I'm not gonna put that down. So integrating that, I'm gonna get V of x is equals to negative f x minus 0 to the 0th power plus RA x minus L over 3 to the 0th power minus omega x minus L over 3 to the 1st power. Oops, that bracket should have been actually right here. Minus x minus 2L over 3 to the 1st power plus RB x minus 2L over 3 to the 0th power plus the moment at the edge raised to the negative 1st. And then the moment at x is equals to negative f x minus 0 to the 1st power plus RA x minus L over 3 to the 1st power minus, I'm just gonna take that a half outside right off the bat. It'll be omega over 2 times x minus L over 3 to the 2nd minus x minus 2L over 3 to the 2nd plus RB x minus 2L over 3 to the 1st plus the moment L of x minus L to the power of 0. Cool. I can plug in L's inside and try and find my RA and RB. I'm just gonna zoom out real quick to here so I could actually fit everything without scrolling. Cool. So V at L plus is gonna equal to 0 is gonna equal to negative F plus RA minus omega, spacing sucks. Just gonna move down right here. Times. Is he picky about writing all integrations? Are you referring, do you have to start with a q of x? I would highly suggest you can ask him that question after the exam, but sometimes I like to skip q and v and go to the m if we're looking for deflection. Sweet, you could go straight to the m if you found your resultants through the free body diagrams and statics. Yes, I agree that might save some time. But if you start in with a singularity and you're gonna solve the entire thing with unknowns from your free body diagrams in singularities, I highly suggest to start with a Q. Just because that's just the beginning of a problem. If you start in one spot that you always begin, you can always be sure that if you abuse of that solution every single time, there should be next to no chance for you to failing in that again, unless you just did some mathematical sign mistake. That's it. Yeah, and yeah, for those, I just do equilibrium equations. Yeah, then you're chilling. As a matter of fact, I wouldn't even start with the moment. I would just start saying that EI of y double prime of x equals to that, and you should be good. Yes, yes, that totally slaps. We can totally do that. Here we're gonna get L minus L over 3, which is gonna get 2L over 3 minus L over 3 plus RB, and that's it. We're not gonna include that moment because it has a negative 1 power, so it is just a 0. That guy is off. And then moment at L plus is equals to 0 is equals to negative F times L plus RA times 2L over 3 minus omega over 2. Do you mind if I integrate, I mean, a square right off the bat? It'll be 2L over 3 squared, so that's going to be 4L squared over 9. And then here it would be L over 3 squared. That you get L squared over 9 plus RB times L over 3 and then plus M. So our M is given, our F is given, and our omega is just omega. The only two things we don't know are RA and RB. Then from here, I would just say that, which one would be easier to substitute for? Doesn't really matter. I would just say that RB equals to F plus omega times this turns to the L over omega L over 3 minus RA. Fun fact is that when I solved of this equation, I was only able to solve it right way if I would substitute it for particular force only. If I would try to go vice versa, I would kind of fail a problem. But in a nutshell, it shouldn't matter which way you substitute. If you do RA first, do RA. If you do RB first, it doesn't matter. Okay. So here, then we get 0 is equals to negative FL plus R. I'll just say that it's 2RAL over 3 minus This will be 3 omega L squared over 18 plus L over 3 multiplied by F plus omega L over 3 minus RA plus the M. And here I would just try to kind of clean it up, make it look nicer and neater before I substitute for F and M, just because too many variables may give you a headache. Negative FL plus, actually this guy would be 2L over 3 RA if I wanna combine them properly. This would be this, and that can simplify to 6. Would be omega L squared over 6 plus FL over 3 plus omega L squared over 9. And then I realized I made a mistake. I actually gonna keep it 3 omega L squared over 18 because it's just easier to combine like terms when you just gonna find LCD. I apologize for inconvenience in advance when someone was just copying down things. I know things changing suddenly is not a great thing. Like terms, FL, FL. This is technically negative 3 over 3 minus 3 plus 1 will be negative 2/3 FL. If I combine loads with loads, this would be I'm gonna put plus right here. This would be 2 omega L squared over 2 times 9, which is 18. Comes up to be negative omega L squared over 18. 2/3 L minus 1/3 L will be just 1/3 L plus L over 3 RA plus the moment. And then from here, I'll just move everything on their side except RA and say that this is 2/3 FL plus omega L squared over 18 minus the moment is equals to L over 3 RA. And then I'm going to go to the givens and say that force is omega L over 6, and then moment is 3 FL, which is 3 omega L squared over 6. So let's see if I can remember that. No, I can't already anyway. This would be 3/2 omega L over 6 times L plus omega L squared over 18 minus, I believe it was 3 FL, so 3 times omega L 6 times L is equals to L over 3 RA. Just gonna double check that. 3 FL and that. Yes. Yes, yes, yes. So, coming up to B, we get 3 omega L over 12, 3 omega L squared, plus omega L squared over 18. Trying to remember if I made a mistake somewhere. Did I combine it right? I did combine it right, so cool. And then 3 omega L squared over 6 is equals to L over 3 RA. Shite. I'm just gonna crank them into the calculator as is. I'm not gonna try and find LCD or anything like it. It will be 3 over 12 plus 1 over 18 minus 3 over 6 gives me a nice looking fraction. Gonna decimal convert that to a fraction. I get negative 7 over 36 omega L squared is equals to a L over 3 RA. L's and L's simplify, and then multiply everything by 3. Just gonna take that and multiply that by 3. I should get a horrible number, but nevertheless that should be negative 21 over 36 omega L. I don't know why my calculator gives me ginormous fractions. If I simplify that by 3, all of them, I get negative 7 over 12 omega L for RA. Okay, then if I plug that into my RB equation, which was right here, so we get FL plus omega L over 3. So RB will be, what did I forget? F, positive F. Yes. Minus negative 7/12 omega L. The F was omega L over 6. Yes. Plug that into the calculator. And I get negative 1/12 omega L. Did I make a mistake somewhere? Because I cannot have resultant forces being to negative. This makes no sense. Yeah, that's what I would assume as well, right? So where did I goof? Ha! Thank you. Let's see if that changes anything. That actually changes a lot. Yes, and we get a positive 13/12 omega L. That looks more like it, which is actually, I would say that's kind of balanced. If RB is positive, this guy is pulling it down. This guy is pulling down, this guy is pulling down. This guy makes it turn this way. So in a nutshell, but that would look like is you would have the deflation is somewhere between the moment applied in my case and our B right here. But yet to keep it flat, RA would have to pull it down right here, along with the distributed force and the F. Makes me ponder a lot of things now about my observation of life. But nevertheless, this is the case. We got the numbers. We can say that we have EI omega double prime of x is equals to negative omega L over 6 x minus 0, and before I make stupid mistake like running out of space, just gonna move that right here. What was that supposed to be? That's supposed to be 1, right? Right. 1 plus RA, which comes out to be negative 7/12 omega minus L over 3 to the first minus 7/12 omega L x minus L over 3 to the first minus omega x minus L over 3 to the first, actually to the second, minus x minus 2L over 3 to the second. I believe this should be actually omega over 2, right? Right. Plus 13/12 omega L minus the moment in terms of omega and L was omega L squared over 2 plus omega L squared over 2. I forgot to say that this guy should be x minus 2L over 3 to the 1 plus omega L squared over 2 x minus L to the 0. The question was to determine the maximum bending stress in the beam. Cool. So we don't even need to find this anymore. We don't need to write it in an EI omega double prime because we're actually interested in this. And as a matter of fact, we're also interested in the shear force for that matter, because the maximum bending moment can happen either when you find the actual maximum value of the moment, or the easier way to trick it is when you find the shear being 0. That's usually when maximum like point happens. Cool. Sweet. So how do we draw our stuff based off of this thing? Well, you will kind of sort of have to dissect it into the chunks anyway, but here is how I do this. And I'm just gonna show an example on the shear first. So I like to write out all the places where I have changed and stuff. So I have changed L over 3. I have changed in 2L over 3. And I have like ending point at L. So somewhere, so let's see, this is kind of, let's try to distribute it evenly. 2, 4, 6, 2, 4, 6, 2, 4, Cool. Sweet. So if I write this out as shear, and I do this in terms of omega L everywhere, all I gotta do is just be concerned about my places of like of fractures, my bad, of a 1/6, 7/12, yada yada, and stuff like that. Good night. Yes. So yeah, if you guys do need to leave because it's too late for you, I do feel a little bit exhausted myself too. I've been talking for solid 2 hours. So yeah. The negative 1/6 would be somewhere right here. Negative omega L over 6. We're gonna maintain that up until we get to L over 3. Past L over 3, we're gonna drop to another 7/12. So if this is 2/12, we're gonna drop another 7/12 right here. Omega L. And then here, I'm gonna be keep on going until I'm gonna get to this position. So this is gonna be a 1/3. So it'll be negative. Oh, actually, this is not 7/12. This would be negative 1 over 6 minus 7/12. This comes up to be negative 7.5, which is negative 3/4. Cool. And then here is going to be a straight line because of the x, and it's going to go from L over 3 to 2L over 3. So I just draw the final destination for here, and then I just draw a whole line. So I get negative 1 over 6, negative 7/12 minus another 1/3. And I get a quarter. Ah, crap. I just accidentally multiplied them. Minus 1 over 3. Turn that into a fraction. Hopefully, yes. I get a solid negative 13 over 12 omega L. Let's call that being somewhere right here. And what's great about it is that in a shear, this guy actually equals to 0. So if this guy has to get up to a 0, otherwise I have some shear left over, and there's nothing that's gonna cancel it off for me. And I realize that my stream that I'm recording doesn't capture the video right. Here we go. So then, something like that. So then I get exactly 13/12 omega L. Gonna go up to here, and then we're gonna go 0. So unfortunately, I didn't get any moments, any shear being is 0. So the only solution for that is that when I actually calculate my moment at specific places. However, I can almost guarantee you that that's gonna happen somewhere right here, because the moment is just a summation of the area. So if we draw another, I know that everything's going to be below 0, so I'm just going to draw it about this long. I'm going to drop the line going from here to here. 2, 4, 5, 2, 4, 5, 2, 4, 5. This would be a moment at x and at x. And then for the moment equation, I'm going from 0 to omega L over 6 in the negative direction. So it's literally this area right here would be what I'm gonna end up having as a value. Or actually not, because it's not L, it's just omega L over 6 times the distance, which is L over 3, so that's negative 1 over 6 times 1 over 3, so I get negative 1 over 18, right? So value right here will be negative 1 over 18 of omega L squared. That's going to be right here, so this guy is going to go directly to here. And now to find the other value up to omega L right off the bat. Actually, I'm not going to be able to do that. It'll be just, I'll find out the value right here, somewhere right here. I'm just going to plug in 2/3, so negative 1 over 6 times 2/3 minus 7 over 12 times this is going to turn into a 1/3 minus 1/2 times 1/3 squared. Right? And I get somewhere of negative 13/36, which is, yes, bigger than my previous answer. I got spooked a little for a second. Negative 13 over 36 omega L squared will be right here. So that's going to go as a parabola, like this. Then if I plug in 1/2, I should just get a L. If I plug in an L, I should end up with just a 1/2. So negative 1 over 6 times 1 minus 7 over 12 times 2/3 minus 1/2 times 2/3 squared minus 1/3 squared plus 13 over 12. Oops, that's in parentheses. Let's keep it outside. Plus 13 over 12 times 1/3 I do not get my 1/2 for some reason. What would this turn out to be? Don't really get a half, but I should. So I did make some calculated mistakes somewhere along the way, I guess. But in a long term, this should just end up being flat line, and then this should end up being exactly whatever this value right here is. So if I would have calculated this guy correct, and this guy actually should be exactly a half. If it's not a half and my moments don't end up being a 0, I made a mistake. So moment max should be a 1/2 omega L squared. Okay. Any questions about this overall? I know it took too long to derive and to show every single step. Hope and pray that that's not going to be on your exam. That's all I get to say. If there's nothing to say, it's either means two things. It's either I did a great job and you guys have no questions at all, or I did such a horrible job that you guys don't know where to begin in a first place. Mm-hmm. 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 Yes, exactly. Very depends on how the crowd feels like. I am a third down to my energy drink, so it probably means that I'm gonna be staying up as long as I don't need to stay up. Mm-hmm. Homework two. Are you about Springs? I think Springs was homework number two, right? Cool. Yes, 3-8. I'll say don't do it, but I did for sure. Do not try to derive an equation for forces do a written exam. It's not worth of your time. I did that because I tried to re refresh myself on how to work with dynamics equations. If you guys are taking dynamics, you will learn that at some point, usually closer to the end, when you guys gonna learn oscillations. Someone said, brought in me Putin. He says, yeah, this is a lot of work. Hope 60 minutes is enough. Hope 60 minutes is enough. Hope that he's not gonna do anything like that. But if you do get something like that, just usually, I know this guy doesn't allow any cheat sheets, and I'm gonna say probably stick with the rules mostly because this is being recorded and someone probably gonna leak it to the teacher. uh, but yeah, just be prepared. Okay. Uh, about springs. What exactly? But okay. Usually with these guys, you just find a equation in a book, or you just commit it to a memory, and you just plug and chug. I believe tattoo gun costs about $100 if you want to engrave it on you. No worries. Mm, so no cheat sheet. Uh, I checked the syllabus. I'll say that. I'm really trying to play safe here without being a devil's advocate. I'm sorry. um, yes. So yes, you guys do whatever you if you feel like doing as far as your consciousness keep being clear, and you don't end up like that one guy who's gonna come to him at the end of the class and sob to his shoulder, be like, "I'm sorry, sir, I've cheated your whole uh class." Okay, so of you guys adults, you can figure out how you wanna to take exam. Uh, I will definitely look over them right before the exam, and I will abuse the short-term memory. Yes. No. He. Yes. And my experience with him in his exams were such that usually I either wake up mid of his exam or I use up all the time and the canvas closes on me the exam just as I was about to submit it. So I had good crap of a luck. I hope you guys don't have that at all. I know, such is life. Uh, I remember looking over the chat of the class the other day. There were a couple of questions about the bearing stress and a breakout, not a breakout, but when you would literally, God, what's his name? But the e the uh, the shear stress. Do you guys need help with that at all? Yes. So great. Good thing that I've asked, huh? Oh yeah, can I go over that real quick? Cool. Yes, I can definitely go over that real quick. So how should I put it? I'm just gonna grab the general um, example off of my memory that I saw in a book, and those are mostly double jointed beams. Okay, when I would look at the beam, I would have a beam right here. Oh, that's ugly. Just gonna do this. I would have a beam right here, and then I would have another beam being connected right here, like so. Ting, 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 ting. Where the pin would go through here like that. Okay, so let's call this guy, we're gonna call this depth. So D from here to here. And then if I look at it from the other side, so if I would rotate this like so, 90 degrees, I would see something among these lines. Actually, even better, I'll just say this. This is where the in-depth part is, like that, and the beam is gonna go like that. And I'm gonna zoom, and here's the pin. I'm gonna use the same color. Here's the pin. Okay, such that, actually I'm gonna put it right here so the radii would match. So I have radius out, and I have teeny tiny radius in. Okay, so if you pull too hard, this guy eventually is gonna crack, and you will end up with something like horrible. So good that I did not go to the art school. I would suck at art school. Although I do have the music degree, but that's another story if you guys really want to hear how that did not go well. Something like that. Cool. So here's the pin, and the leftover of the piece is just gonna be dangling right here on top of it. And that is the worst case scenario, right? Because the larger cross-sectional area is, then technically, so the stress is the force divided by cross-sectional area. So the larger cross-sectional area is, the smaller of a stress you will need. So it would definitely break somewhere where cross-sectional area. So if I would write it down like so in a 3D shape, like that, like that, like that, like that, where this guy right here is cross-sectional area. The larger the cross-sectional area is, the smaller the stress you will get. Therefore, if you will pull too hard, you're gonna break it, and you will break it right there. So how did the problem solve it? Well, the problem solved it this way. If I look at that, and I look at that, I need to find this length right here, this L. And since I know the depth already, I'm just gonna find my area of rectangle, and that's pretty much it. So if this is the R outside, and then this is R inside, the length, no, that is absolutely not the answer, because I just formed a triangle where I have small r, big R, and an L right here, and then L is gonna end up being square root of the R square minus small r square, nowhere near being the same as the R minus small r. I saw that in the chat. I thought so too. Took me a bit of a moment to figure out why I got a wrong number, and that came to mind. Okay? Granted, I probably also asked a couple of people around and used some sources. I just turned myself in on a video, but who cares? Yes. No, that's just the length, right? Because we acknowledge that the depth is this, and then the length is this, right? The depth was given us from a problem, okay, and the length we had to find, okay. Now, since I have double jointed thing, right, my shear stress is gonna equal to the force divided by 2 over the area, okay. But then the thing is, since I have a double shear, I'm gonna break out in 2 points, right? I'm gonna break right here. Oh, I'm gonna use different color. So I'm gonna break right here, and I'm gonna break on this side as well, right? Then the shear stress of a breakout, I'm just gonna say break, is equals to the shear stress over 2, which comes out to be force over 4 times cross-sectional area, which comes out to be force divided by 4 square root of the r squared minus small r squared times the width, or a depth, okay. So even if I did say I have a single up-in joint, okay, so let's say there is none of this side, the pretty much the breakout shear stress is definitely gonna be the shear stress divided by 2. The breakout shear stress is gonna be shear stress divided by 2, and the area will be the area at which is gonna be breaking off. Okay. All right. I was hoping I'm not gonna lose you on that one. I got approval. I did not lose you on that one. Don't blame me if you guys don't do well on exam. Joking. Oh, I know. Good night, Diana. Wait, why is it 4 again? Because I have 4 cross-sectional places where it's gonna break, right? So if I draw it out in 3D, and when you guys see me on campus, don't laugh at me, okay? I already screwed it up. Done, done, done. Screw it. Since I have connection right here and right here, I'm gonna have 2 of these guys break out. Okay? And then both of these guys gonna have 2 sides, they're gonna have grinding shear against them. Okay? It's gonna be this guy and this guy. Okay? The problem in a homework, I believe it was 2, because we simply had just a single shear problem, like that, like that, like that, going like that, going like that, and like that. Here was our ball point, and when too much force being applied right here, right, it's gonna cut it out like so. I should have used the other color. The one guy will be on that side, and then the other guy will be going on this side, right? So it's gonna be looking like this little piece. The solid right here. And then another part, I'll do it in dash and right here. Right? So it'd be this guy and that guy. So since we had single shear, we're gonna have only force divided by 2 times this cross-sectional area. Yes, exactly. It's 2 for that one because it's one bracket part. Correct. I should pay attention to the chat before I jumped into explanations. Hi. All right. Good night. Kind of did promise that I will go over one solid a problem from a book, but I lost half of people and it is already tomorrow. This video will be available for us to watch later. That is the plan, unless I will really look over that and realize that I should never be a streamer and give away all of my equipment and yeah, never even bother do that again. We can do another one. Same one other day before maybe. Unfortunately, no, we cannot because I also have another exam on Monday, and I do need time to prepare for that as well. I'm sorry. All right. Good night. Yeah, dude. Okay. Oh, that sucks for someone who gotta be up at 5 a.m. I do not envy. Good night. All right. All right. It's been fun. I hope this has been educational for you all. Good night.